Hello, everyone. For this lecture series, we're going to be covering concepts that are discussed in Chapter 6 of our organic chemistry textbook. So this chapter reviews concepts of chemical reactivity and mechanisms. So let's take a look at what that looks like. So you've probably heard of the term enthalpy in the past. It's designated with this symbol, this delta H. So whenever we're referring to enthalpy, we're referring to specifically the energy that is contained in a bond, right? So we have this bond enthalpy that we'll discuss. And in order to break a bond, we have to add energy, right, to break this bond. And then when bonds are formed, we'll see that energy is released. So we can actually calculate using values for bond enthalpy dissociation, they're called. We'll be given a table, and we'll actually be able to predict whether or not a reaction will be endothermic or exothermic. So there's two different ways that bonds can break. We can have homolytic cleavage, or we could have heterolytic bond cleavage. With the homolytic bond cleavage, we see that one electron goes to each of the atoms that are bonded, right? So the X receives one of the electrons in this XY bond, and then the Y receives the other electron. And that's, again, homolytic bond cleavage. So the same, right? Homo, we know the root means same. Lytic is a way of saying something is broken. When we have heterolytic, that means that we get a different number of electrons on each atom. So we can see here that our X is now positive or becomes a cation because it is lacking an electron, and our Y has received both electrons. So you may notice that there's different arrows to indicate the movement of electrons. When we have one electron moving, we use what's called a fishhook or a half-headed arrow over here. And then when we're moving both electrons in this bond to the Y, we would use a full-headed normal arrow. So this bond dissociation energy that we're going to refer to corresponds to homolytic bond cleavage. So keep that in mind, that all of these bond dissociation energies will be for the homolytic type. So here's some common bond dissociation energies that are affiliated with these homolytic bond cleavages. So we have H2, right? This is our first example here. H2, when that results in a homolytic bond cleavage, the amount of energy that is needed to break this bond is given per mole. We have 435 kilojoules per mole. We really won't utilize this other unit, kilocalories per mole, this semester, but kilojoules per mole, you should become more familiarized with that unit. There's also some other common bond associations, like the HO bond in water would be 498 kilojoules per mole. So we'll look at some examples in a later video where we have to actually solve for, whether or not a reaction will be considered endothermic or exothermic based on the net result, the delta H at the end of the reaction, right? The enthalpy change overall. So here are, again, some more carbon-carbon bonds that we'll also see listed on our bond dissociation energy table, table 6.1. And then we have down here some of the halogens, some of the diatomic halogens, such as F2 or Cl2. Sometimes those are needed as well. So this should be a little bit of a review as far as what the terminologies endothermic and exothermic are referring to. We have multiple bonds, right? Bonds that need to be broken and bonds that will be formed. So we need to break bonds and then form bonds to create our products. And if the net result in the enthalpy change is a negative value, right? So we have a negative value, that would indicate an exothermic reaction, right? So the energy gained by bonds formed exceeds the energy needed for the bonds to be broken. So a negative amount of energy you could think of is needed to power this reaction, right? We don't need to put in more energy than we gain. So more is released. With an endothermic reaction, we have to put in more energy than is released when the bonds are formed. So this would be given a positive enthalpy change value. So delta H can either be positive for endothermic or negative for exothermic. And we can see that there's also some description about our products here. So products are more stable than reactants when we have an exothermic reaction. They're at a lower energy. And we'll look at some of these energy diagrams that relate to these types of reactions. And then an endothermic product would be less stable than the reactants. So these are the energy diagrams for exothermic and endothermic processes. And we can see that with an exothermic reaction, our product's energy, our reactant's energy starts up here, and our product's energy is way down here. So the change in energy shows us that, or rather the change in enthalpy shows us that there's a negative change in energy, and our products will be much more stable than our reactants. And that's always the case when we consider the energy of our molecule. If it's at a lower energy, a lower potential energy, then we consider that a much more stable molecule. And then we see the reverse here when we talk about an endothermic reaction. Our reactants are down here in the energy diagram, and then our products are at a much higher energy. So this is what we were referring to when we said that the products are less stable. We need this positive change in enthalpy to reach our product, right, from our reactant. Let's see here. So we also have, we've discussed this, the sign of our delta H, the sign of our change in enthalpy. Again, we correlate positive change with an endothermic reaction where we have to enter in energy to get the process to continue. And then we have our negative sign, which is associated with an exothermic reaction where energy can exit our system after the reaction occurs. So the energy diagrams, they show us the potential energy, right, on our y-axis, and then what's called the reaction progress or the reaction coordinate is commonly described on the x-axis. So, right, we have our y here with our potential energy, and then we have our x-axis down here with just the progress, right? So as our reaction progresses, it goes forward on the x-axis. So here is our bond dissociation energy table that we can utilize for some of these practice problems coming up. On the next slide here, we see this reaction, right? So we have our hydrocarbon over here, right? So if we were to write the molecular formula for this, we'd have CH3, CH2, CH3, and that's propane, right? We have 1, 2, 3 carbons, so that will give us propane. And then we have our bromine, our diatomic halogen here. So this, we know there's a bond between the two bromines, and here we're going to focus on the bond that's broken, which will be this carbon to hydrogen bond. So that's what we're going to see is broken in red, this bond here and this bond here. And then let's change colors. So the bonds that will be formed will be this bond here, and then the bond between the hydrogen and the bromine that are left over. So in order to find our bond dissociation, our enthalpy change overall, we take the bond dissociation energy of our broken bonds, right? That's how much energy we have to put in. And then we subtract the bond energy from the bond dissociation energy of the bonds that are formed. So if we went back to that table, we would see that the CH bond that we're referencing in our first molecule, right? So the bonds that need to be broken, we'll look at first. That CH bond is 397 kilojoules per mole. And the bromine-bromine bond is 193 kilojoules per mole. So we would add these together, right? So down here, that's the sum of our bonds broken. And then let's go to our table again, right? We metaphorically are going to our table because the information's right here. So we have our CBr bond that's formed and our HBr bond that's formed. So we add those two values together and then we subtract the sum of those. So our net change in enthalpy is given over here. So we see that that is a negative value. So overall, this reaction would be considered exothermic. All right, so that's the end of this tutorial. We'll pick up with section 6.2 next time.